Welcome to the Neural Implant Podcast, where we talk with the people behind the current events and breakthroughs in brain implants in an understandable way, helping bring together various fields involved in neuroprosthetics. Here is your host, Mladen Juracek.
Hello, everyone, and welcome to the Neural Implant Podcast. Today's guest is Dr. Vasiliki Giagka, and it's not how it spells, or Vaso also is how you go by, and you are at TU Delft and also a team leader at Fraunhofer IZM in Berlin. Okay, first of all, before we start, how do you do this? Like, how do you work in Berlin and The Hague in the Netherlands at the same time? Those are two different places.
Yeah, so first of all, thank you for having me. Yeah, I commute. I travel back and forth. Obviously, during the pandemic, this traveling was not so much. But generally, so part of my research team is based in Berlin and part of it is based in the Netherlands, in Delft. And I really like the way that it's organized. I can explain to you more if you want. But yeah, the way we do this now is that we have invested a bit on equipment that we use in order to have all meetings virtual or hybrid. So we make sure that the Berlin or the Delft part is anyway, in any case, has an opportunity to participate if the meeting is held at another location. And we organize group activities that everyone meets each other with. There are people that have spent time in both locations, so they act as a glue a bit between both locations. Somehow it works.
Yeah.
Started this dual appointment in 2018. In the beginning, I have to admit, it was also new for me. I didn't know whether this would work, but yeah, I have found that it actually works better than I thought.
Yeah, that's really interesting. And then now for listeners, I guess we'll finally introduce you. You work on basically packaging for neurostimulators, wireless power transfer, implant miniaturization, microsystem integration, packaging, encapsulation. So it's funny, we were joking before we started recording, this is what I'm working on as well. And maybe one of the only few people in the world that thinks device packaging is sexy. And so why especially device packaging? That's the most interesting part is the electrodes and the electronics, isn't it? Why packaging? Why just this case, this cover? Why are you working on the box?
So in our case, I think it's not a box. Let me take it from the beginning. In my lab, we have this vision for active neural interfaces that operate in a network inside the body in a closed loop manner, are able to be wirelessly powered, communicate to each other. That is not new. That's not only us that have this vision, but this then network of devices is capable of delivering therapy and also help us understand how our bodies, the neural pathways in our bodies, both as a therapy and as an investigational tool. This is the overall vision, right? So there are a lot of people in the world that are working to realize this vision. And in my team, we have set with this background, we have set three specific goals. The first one is to reduce the size of active neural interfaces to millimeters. The second one is at the same time, we want these active implants, these active neural interfaces, to have a lifetime that can reach decades. So minimum, reducing the size, increasing the lifetime. And we want to increase eventually the specificity at which we interact with neural tissue. So to realize these three goals, the first two, as you can already see, it is for the first two, it is very important. Packaging is very important. Packaging, the way it's done at the moment, or the way it is conventionally done in devices that exist in the market, is that all the electronics are placed in a large hermetic housing, which is the main limiting factor in terms of size. Really, to miniaturize, to reach this millimeter size that we envision, this is not strategy we can continue following. So this is why we explore conformal coatings. We call, and after a lot of thinking, we have decided to really stick with the term conformal coating, because we assume that there is no air gap between the electronics and the protective layer.
Okay.
Yeah.
So yeah, normally these packaging integrated pulse generators or something like this. They're pretty big. I don't know what that size would be. I don't know, maybe the size of a plum or something like this, like the diameter of a plum and maybe a centimeter thick or something. So it's a big disc. And so you're going from something about this size to how big? What's the size of your guys' device or packaging?
So minimal. It's only coatings on your components. So we design and fabricate active neural interfaces, meaning neural interfaces on flexible substrates with integrated electronics. In the ideal scenario, we would have single chip implants. So all the electronic functionality would be designed and integrated on a single die. Of course, that is the ideal scenario. That is, will never be like this. I don't know, it might be, but in several cases, it might not be possible because obviously you need some other components for wireless power transfer. For example, an additional antenna or a coil. But there are also approaches where this is implemented on a single chip. But so in the simplest case, you can imagine that you have a single silicon IC, silicon integrated circuit, coated with conformal coating. This is what our driving factor. This is the scenario that we have in mind when we are looking into conformal coating. So the packaging in this case adds minimally to the overall area or volume of the implant.
Yeah, really. So it sounds like almost you'd maybe add a few nanometers or microns of some kind of coating, which is negligible, and you'd get rid of one completely get rid of one whole component, which is honestly the biggest size. So then the neural implants can be more what maybe the public general audience might imagine is just literally just something that goes into the brain and not all the other stuff that goes behind it. So I want to talk about this network of devices, this mesh that you're describing. This is really interesting. I haven't heard too much about it. Do you want to describe it a little bit more, and how does it work, and why is it necessary?
Eventually, I think this whole idea, there are several people looking into it, especially in the circuits and systems community, where I also started. So my background is circuits and systems and microfabrication. That's why when you look at my work, it has a bit of both. So really at that interface. So in that circuits and systems community, there are a lot of people looking into this because it has a lot of challenges in terms of how do we power the implants wirelessly when they are so small, when they are also deeper in the body, and how we make sure that they can communicate so that we can send information to the implants, send information out of the implants to something external, or also send information among the implants so that they talk to each other. You may want to be able to stimulate at a specific location in the body and record from a different location. And not necessarily only in the brain. It can also be at different parts of the nervous system. You may also need to look at specific other biomarkers inside the body or have special type of biosensing in one location, but then use this as a feedback to regulate your stimulation patterns at a different location. So that's the whole idea of a network of implantable devices that work together as a then implantable interface that has a lot of components that are distributed inside the body.
Yeah, that's really exciting stuff. That's a futuristic view of things, and how we might imagine it, the public audience, and getting input from one and that controls another. And it could be, and it might not even have to be neural implants. It could be blood pressure monitor or glucose or something like this measurements. Exactly. It could be something completely different and all enmeshed in this network. Hey guys, just a quick pause to talk about our show sponsor, Ripple Neuro and Neuromed. If you're a scientist looking to get the best quality data possible in your animal and human ePhys experiments, then talk to Ripple. Get a complete solution for your neuroscience research application backed by dedicated support. Be sure to tell them you heard about it on the Neural Implant podcast. That will really help us out. Thanks. Now back to the show. Yeah, okay. So let's talk about maybe wireless power. What is it? How does it work? Why is it necessary? All this.
Wireless power. Shall we start from wireless power or let's
if there's a better starting point, let's start there.
Since we were in the packaging topic, I was planning to continue a bit there.
Yeah.
And then we can.
Yeah, that's it.
Okay, in that conformal coating domain, I think we've made recently some significant discoveries that we are now, we've been working on this topic for some years now. And so now we're putting all this understanding in manuscripts that we're going to submit soon. But I can already tell you a bit more about what the understanding that we have from this research, from these studies. So what we've seen there, we have investigated how the silicon IC, as I mentioned, one step back, our focus is active neural interfaces. So we are always discussing about neural interfaces that have embedded electronic components. And these integrated circuits, there is a big question mark in the field, how these are going to perform in the body. Are they going to degrade? Is their operation, because this is the main component that keeps the intelligence of the system. And if you don't have now a hermetic environment protecting it, you have a conformal coating, which relies on a slightly different fundamental mechanism. And I will explain this in a second. Then the question is, how will that last long enough? And what happens to the chip? Will the chip performance degrade? So what we've done then was that we conducted a long study in which we employed experiments in the lab using accelerated lifetime tests, but also in vivo, where we studied the degradation, or where we studied whether the integrated circuit performance, the electrical performance, and its passivation will degrade over time. So what we have seen there is that for the duration of this study, the electrical performance of the chips, and now these are active components, including transistors, this will not degrade. So we will not be able to pick up any change in the electrical activity. This insight is very important because basically what it tells people is that, look, if you're targeting short-term applications that are, for example, up to 1 or a couple of years in the body, you don't need to worry too much about how to protect your IC because its performance, electrical performance, is not going to degrade. I will put an asterisk here and I will come back to this point because the electrical performance is not going to degrade, but we have seen degradation in the passivation. This has been documented in the past in the literature. We also saw it, and I will come back to this point. Then the other, however, not all applications are targeting short lifetimes. If we're talking about decade lifetime, obviously this is not sufficient because we saw, as I mentioned, degradation of the passivation. So we expect that for longer durations, at some point, the electrical performance will also degrade. So then is at that point that we need to intervene and take care of the coating. So we need additional protection. Okay, now a couple of things to mention here. I'm only talking about the silicon IC. In your implant or on your implant, I'm only talked now about its passivation. On your implant, you're going to have additional components. You're going to have points. You're going to have pads. So you're going to have all these probably. There are also scenarios where you don't, but in most cases you will. This is a different story. We have looked a bit into this, but you also need to take care of these points, how your assembly or your connections are going to behave. Now, going back to the fact that for longer lifetimes, we need additional protection. There, we need to make sure that we have coatings that can protect this degradation of the passivation of the chip. And there we have, with the years, developed the understanding there are two different mechanisms to protect the degradation of that passivation. One would be to keep all moisture out. Make sure that make sure that you create a package that is hermetic. That is the more standard way, but now in a miniaturized form. And the other one, so for this first one, you need to use materials that are very good barriers to ions, good barriers to water molecules, etc. For the second mechanism that is possible to protect the degradation of this CMOS passivation is based on adhesion. So if we have a coating that has very good adhesion on that silicon passivation, and we make sure that this adhesion is not compromised over the lifetime, then we don't have the conditions that are necessary for the chip to degrade. Usually, your chip, you're worried about corrosion. So in any case, you're worried about liquid water with ions formed close to your chip. That is what you want to avoid. Ensuring using coatings that have good adhesion to your silicon passivation will meet this criteria. In this study that I was talking about, we have used silicon rubber. In fact, previous study in collaboration with University College London, we published about how silicon rubber will protect thin ceramics. Now we took it a step further, and now we have real CMOS devices, and we see that these silicon coatings, if we make sure that they are applied in a proper manner on a clean substrate, will protect for really long lifetimes.
Okay, so basically, so there's two methods: one to make a bubble, a hermetic seal, and I don't know if I understand the conformal coating or the adhesion so much, but that's also essentially creating a hermetic seal, and it's just around this, or is it like a chemical thing, or how does that work?
No, it's really not hermetic. In that second scenario, we use a coating which is a polymer. It conformally coats a substrate, but because it's a polymer, it will very soon be saturated with water vapor. It's not hermetic in that sense, but water vapor is not dangerous, will not cause your metals to corrode. As long as it remains in the form of vapor. The moment it condenses into liquid water, and you have also ions in there, there is where corrosion will start. You are going to start see corrosion. And that is the beginning of the end, eventually.
So essentially, it's like a sponge. It absorbs like a sacrificial layer that pulls it away from everything else, almost like those little packets, the silica packets that they put in, I don't know, whatever, some powders or something like this.
Yeah, it gets saturated with water vapor. That is going to happen because of the nature of the material. But this is not going to damage your electronics as long as it remains in that vapor form.
Okay.
And the condition for it to remain in the vapor form is to ensure that the adhesion between that coating is saturated with water vapor and its substrate, that adhesion is not compromised.
Okay. And then, so what it was sounding like too, that you can use actually both of these methods to get even better, I don't know, longevity out of these, right?
You could think of combining the two. However, in our experience, the more materials you add, the more interfaces you have to study, and the more complex you make your system. And then you increase the likelihood that something is going to go wrong. And if we're talking about really decades, this is not a path you want to go into. Also because it's very difficult to test for decades.
Yeah, definitely. Yeah. So what are some kind of rough numbers? Is one method better than the other? And then how many years of simulated life can one survive versus the other? Yeah. Give us a rough idea of what this looks like.
I'm not going to talk to you about lifetime in the sense of, I'm not going to translate what we've done in accelerated lifetime tests into a lifetime in the body, because that is really not an accurate estimation. And if you want to learn more about this, I really would recommend to reach out to Professor Anne Fusterberg from King's College London, who has been studying this for some time now, and she will tell you all about how the Arrhenius approximation should not be used for this. But so I'm not going to do this direct translation into numbers, and I think let me summarize it like this. For silicon rubber, there exists now silicon rubber, which is just a single polymer, a single polymeric coating, very permeable to water vapor. There exist implants that are in the body of patients for 30 years now. These are the Brindley sacral root stimulators, coated with silicon rubber. There are a lot of conditions that you have to take care of. Like the very important one is how clean your surface is before you apply your coating. And you also have to look into how you place your components. You have to really make sure that your coating is conformal, that you ideally get rid of any air bubbles that you have in your polymer. But if you design it correctly, that's what I'm trying to say, it has this technology that relies on maintaining adhesion alone, has the potential to reach equally long lifetimes as a big hermetic housing, so decades long. And that is, we've seen this in patients. However, what this technology cannot offer is a prediction of that lifetime, because you can't test it in the same way that you test with hermetic packages using a helium leak rate test.
Okay. Yeah. Okay. Another thing, we're talking about decades of testing and everything like this. It doesn't look like you've been working. You look young. You don't look like you've been working on the same project for 4 or 5 decades. So how do we test it? How do we do the accelerated testing to be able to simulate a human lifespan?
This is a good question, and I don't know if anyone has an answer on this. At the moment, we use accelerated lifetime tests. We increase the temperature to a certain degree, not very high, because then you introduce failure modes that may not exist in the body. So we increase the temperature of a bath, which has usually saline, PBS, and we also use another form of acceleration factor, which is applying electric field. That's another thing that I didn't talk to you yet about, but that's another very, in fact, important parameter that you should be looking at. So the whole idea about why the chip is the integrated circuit is the component that we worry about the most is because the highest density of electric field is going to appear there, because you have very small, narrow tracks, and you have high voltages, high currents, so large electric fields. And this electric field will kill your device if not properly protected. So that is another form of acceleration factor that we use. In our study, the study that I mentioned, in our acceleration study, we have continuously biased our test structures at 5 and even 15 volts for a year. There are other things that you can use, other reactive species, but we have not used these in our setup.
Okay. Yeah, actually, I haven't heard too much about the electric field, and that's pretty interesting. And then 5 and 15 volts, that seems pretty high. Isn't that outside of the water window in saline? Wouldn't that cause bubbles, or is that just a bias?
Yeah. So look, now you don't have any electrodes in this case, right? It is we only apply this to test how the adhesion of the coat, how this electric field will affect the adhesion of the coating to the top passivation layer when it appears at interface.
Yeah, this is very interesting. Yeah, I think this is the future. And honestly, this is the packaging and everything is really what's limiting a lot of neural interfaces. That's my opinion. Electric design,
often
whatever.
Overlooked. It
Exactly.
is often overlooked. We already discussed that I have 2 affiliations. The Berlin one is the Fraunhofer Institute for Reliability and Microintegration. So there is a lot of background and understanding in this packaging for electronic packaging for different applications. In my team, we are the ones that are looking into this topic for biomedical applications, but there is also a lot of expertise and know-how to harvest around from in this domain for other applications like automotive and applications that involve electronic components.
Okay, so now you also work on the wireless power delivery, wireless transmission. How does this work? Why is this important? Yeah.
So obviously, for implantable devices, you can't have one solution is a battery in a scenario that I discussed would never work. We don't have a hermetic protection to keep the battery in. And apart from the fact that it also adds volume to your implant. Let's assume now there are approaches that we could consider to miniaturize the battery, but such a battery would also not work with the conformal coatings that we are looking. So we really need to have a wireless power transfer for the implants. First of all, I have to say, we are trying to push the technology front in different aspects. In some applications, you can't get around without having a battery. For example, if you're developing an implant which is meant to treat or deal with life-threatening conditions, there you can't rely on perhaps wireless power link that perhaps at the time, at the instant that you want it to work, is misaligned or is broken. 1 minute later it works, but when you want it to work, you compromise the life of the patient. So in that case, no, you go with a hermetic approach, you go with your big housing. So it's clearly a different application. But for these kind of implants that we are considering, which are not for life-threatening conditions, you may want to stimulate a few minutes a day or perhaps even longer, but so you have some minimal energy storage on the chip. You can sleep power it and then store this energy and use it during the day. And then when you have the next opportunity, you can wirelessly power it again. This is really an approach that would work. And there we are looking. So people have been looking into inductive power transfer. That is not something that we have looked at. We have been investigating ultrasound for this. And in fact, in my team, we have now 2 different activities involving ultrasound that we explore, also as part of a large project that we are at the moment working on together with some other European partners. And we use ultrasound to power neural implants, neurostimulators in particular. So electrical neurostimulators, but then we also explore ultrasound to increase the specificity at which we interact with the peripheral nervous system. So we use ultrasound for neuromodulation, but then in contrast to the common approach where ultrasound is kept external, we try to bring it inside the body. So it is on an implant now. And we are looking into ways to use this to increase the selectivity of neuromodulation for the peripheral nerves. So there, what we have been working on is creating an implant in the form of a cuff, which has an array of ultrasound transducers around that cuff. And these array of ultrasound transducers, we drive them with ultrasound, but introducing time delays at the different elements. So in a phased array manner. By doing this, we can create small focal spots inside. If you consider that this is a cuff that is wrapped around one, we can, by creating a small focal spot or target specific or individual nerve fasciculars or even single neurons within these nerve fasciculars. So that's the whole idea.
And I think this is maybe how you're able to do, so using this wave superposition, you're basically like having the peaks line up in a certain spot at a certain time. I think this is maybe how you're able to work in Berlin and Netherlands at the same time. You're doing this superposition wave, two places at the same time. Sounds like there's a lot of overlap with what you do. But that's really exciting stuff.
Technology.
Exactly. That's really exciting stuff. And I've always thought about this, and that this is something that could be done and really can't be done so much with electricity or electrical signals, because it doesn't have the same waves and everything like this. And
exactly. Usually with electricity, you can become a bit more specific, but then normally if you have a cuff around the nerve, then you stimulate everything around that cuff. Or if you really limit the intensity of the stimulation, you reach the structures that are at the periphery, but you can't really be selective. Then you have to be invasive to the nerve. There are different types of electrodes that can penetrate the nerve, is the life and the time electrodes, or then you have to compress the nerve, which is possible. But now we are, with ultrasound, what you would gain versus electricity is that you can really then dynamically change that focal spot. So select which fascicle you want to tackle, or which neurons even. You can really reach that type of resolution. You could. We are not there yet, but principally you could, and adjust the location of that focal spot dynamically, and also in the in the volume. So bring it forward, bring it backwards in the 3 dimensions.
Yeah, that's really cool. Okay, but neurons fire with electrical signals, and you're using ultrasound. So how does that work? Why is it able to work?
Yeah, I don't know. I don't know if anyone really knows. I don't know if we really fundamentally yet understand this mechanism. There are different hypotheses. I'm certainly not the one that has investigated myself this, but there seems to be mechanosensitive ion channels that are modulated with ultrasound. But even voltage-gated ion channels seem to be modulated with ultrasound. So the exact mechanism, I don't know if we really understand, but it seems that we are capable of activating and blocking neural activity with ultrasound. Now there is a debate whether it is mechanical or thermal effects, and that seems to be, I think we don't understand it very thoroughly yet, as far as I know. Yeah. So we don't have that deep understanding as we have with electrical stimulation. But there is a lot of work in this domain nowadays, and more fundamentally understand how ultrasound is able to modulate neural activity.
Okay. And then how does the power usage compare with electrical based cuffs? Is it more? Is it less?
Yeah, that is a very good question. That is actually one of the main limiting factors, I would say, bringing ultrasound inside the body. You really need a lot of pressure in order to stimulate, in particular, the peripheral nerves because of the myelin sheath. That's the main one of the main bottlenecks that we have. If I would have to compare, I don't know numbers, but but the electrical stimulation it's definitely more efficient.
Okay. Yeah, but I guess it doesn't matter if you have an external source of power and it's not running off a battery, then it doesn't matter. I guess there would be a heat issue, heat transfer, something like this, but yeah, there's ways around that too.
Yeah. I think if you look at it you have to take it step by step, right? If in this case, what we are trying to achieve is increase the resolution at which we can interact with the peripheral nerves. This we cannot do now in any other way. So we have to live with the power demands that this technology requires. Now, later on, once we have achieved that, we can in parallel look into how to make it more efficient, but step by step.
Okay. So yeah, let's talk about your graphene work.
Yeah. So one more thing that we're trying to do is to make our neural interfaces more compatible with modern tools that neuroscientists use to study neural interactions. And for this, graphene seems to be a very useful material due to its optical transparency, because then you can couple it with imaging techniques. So it gives you the possibility to look at whatever is below the graphene, and also because of its electrical conductivity, use it to either stimulate or use the graphene as electrode either to stimulate or record. There's some literature using graphene for neural interfaces, and there are a lot of really great works out there that have demonstrated the potential of graphene as a tool for neuroscience. For example, to allow for concurrent optogenetic stimulation and neural recording at the same location. So what we doing in this domain is that with my colleague in Delft, Dr. Stijn Vollebrecht, who's really the expert on graphene, we have been working on developing graphene electrodes, which we couple with flexible substrates, and we couple with substrates. So our unique approach here is that the type of graphene we use and the fabrication method that we use. So as opposed to growing single layer graphene and transferring it on a wafer for further processing, we now instead use a monolithic transfer-free approach where the complete implant is manufactured on the same silicon wafer substrate. This allows us to have multi-layer graphene, which we believe due to its multi-layer nature exhibit such storage capacities that are higher than its monolayer equivalent, and also higher than those of opaque noble metal electrodes. So now, with this, we can have an implant that can be easily batch manufactured with high yield and has great stimulating properties, is compatible with MRI, shows no recording artifact during optogenetic stimulation, and is completely transparent, so it allows for imaging of the tissue at the same time. For now, our implants, these graphene implants, now we are at the stage with this work that we have managed to manufacture and characterize these. We are getting into the phase now from September to test also its compatibility with cells. And then the next phase, currently these graphene implants that we make are passive. But as I mentioned, our goal generally is active neural interfaces. Then for now, we need external electronics to drive the electrodes. But because of the monolithic fabrication approach that we have followed, the integration with electronics we expect will be much easier. And this is, in fact, something that we have already started working on, and we are currently investigating.
Yeah. That's exciting stuff. Yeah, graphene is a very exciting material and has a lot of superpowers, like you said. And because it's carbon, it helps with global warming if you use it. Yeah, that's really cool. And then for all of these three kind of thrusts that you're doing, these three areas that you're working on, these all seem like very good candidates for a spin-off company or some kind of patents and everything like this. Is this something that you had thought about? Is this something that's in the works, startups, all this kind of stuff?
So for now, that is not something that we in my team are looking at. We are not intending the technology. So let me explain it like this. In fact, having an affiliation with an academic institution, TU Delft, and a research institute as Fraunhofer brings me and my team at that interface. Which is actually a very fortunate position to be in, because we can work on understanding the more fundamentals, which are then very important for the work that we do at the university. But then, because of the affiliation with the Research Institute and Fraunhofer Research Institute that focuses on applied research. So we also work on market relevant problems. So we collaborate a lot with companies, small and medium companies, or even large companies. And our goal is to bring the technology that we develop, whatever we develop in Delft, that has a potential to be useful in the industry. We can then develop it further at Fraunhofer. There we can do things like packaging investigation, more long-term studies, which are not so well suited for a university environment, but then we can do this at the research institute, and then bring it at a readiness level that we can then transfer the knowledge that we've generated to companies. So we see ourselves a bit more like assisting companies that are active in the domain of neurotechnology to start giving them access to technology and know-how and expertise that, because they are starting and they have a different focus, perhaps they don't have the necessary expertise for all the components of such a system, but there we can support. So this is how my team is organized. So we are the aim of our aim is not to create a startup ourselves, but it is really to help this ecosystem in this way through Fraunhofer.
Yeah, so actually, I guess the audience doesn't know that I did an internship at Fraunhofer as well. The same one, IZM, same one in Berlin, same building maybe back in 2012, I think, 2013, something like this. And I definitely saw this too, is Fraunhofer is like Battelle in the US. Battelle is a similar situation where it's in between companies and universities. It's this bridging the gap. And so you're a little bit at the basic in, I don't know, like developmental stage, maybe the egg stage. I'm a duck farmer, so everything's eggs and everything like this, maybe to the chick stage. And so you're going to the middle. And the audience actually might not know I'm a duck farmer. And I was just showing Vaso my new babies, my new duck babies that are running around now. But yeah, that's very interesting. Yeah, now I think this combination, this affiliation in both of them makes more sense. And so if there are 3 steps, step 1, university, step 2, some kind of research institute, step 3, startup, you're in between step 1 and step 2 versus being only in step 1, only in step 2, or only in step 3, something like that.
Exactly. And it is a fascinating place to be, really, in between these 2 steps, as you described, because you get the good from both worlds, and you get the advantages. You can harvest expertise, understanding from both worlds, let's say. So you can really work on market relevant problems, but then you also have the space to look at them more fundamentally and innovate and add novelty, and then bring that novelty back. So it is a back to the market, let's say, or to the industry. So it is a cycle that is like closing that loop.
Yeah, that's really exciting. Yeah, cool. Okay, so I like to ask some standard questions to the guests, and one of my favorite ones is, if you had unlimited funding, what would you do?
Very interesting. If I had unlimited funding, I would. So today we have already touched upon several topics that are also discipline-wise, one might say, not the same. Let me put it like this. We touched upon wireless power transfer, we touched upon ultrasound, which involves physics, we touched upon packaging, material science, electronics, circuit design, etc. So if I had unlimited funding, I would really now delve into all these topics to study them more thoroughly and more fundamentally, each at its own discipline. Essentially, this is what I'm trying to do with limited funding. So I will get there not now, but in 20 years from now. But if I had unlimited funding, perhaps I would bring this 20 years forward to 5 years.
Yeah, that's funny. Yeah. Make your own, force this to become one discipline. That's actually really funny. It's so important but I agree. I think this is, again, what we just hinted at before. This is what's holding back the field, I think. And this is one of the most important things. But yeah,
it is exciting because it's an interdisciplinary field, and you need the depth in its discipline in order to be able to push the state of the art. So you need a lot of communication and a very good understanding of the other disciplines. So you need that interaction with the other disciplines, but you also need the depth. And funding is important to realize this. Yeah,
sounds good. Is there anything that we didn't talk about that you wanted to mention? This has been a pretty comprehensive episode.
Is there anything? Not really. I think we've covered everything. I just wanted to, No, I've enjoyed it very much. So thank you very much.
Yeah, thank you.
Hope you enjoyed the show and were able to learn something new, bringing together different fields in novel ways. Until next time on the Neural Implant Podcast.